Hi, welcome to the part 2 of classification problem. In this, we'll discuss probabilistic classification. Right. For probabilistic classification or in any classification problem, we are given a set of classes C, which are denoted as C1, C2, if there are K classes. Okay. Uh, we're given a data set D, which is made up of Xi, Ci sets. For let's say there are n examples 1 to n, right? And where each xi is then further consisted of features and so on, right? So if we have a description of data like this, the goal of a classification problem is, if you encounter a new data point x star, we have to find the or we have to predict the best class. Right, in this case, the best means the most probable class. Right. So what we need to do is we need to find the maximum a posteriori such of a problem such that ck given x star, that this value is max. We want to find a class k or the item k for which ck given x star, this probability is maximum. Right. We are most interested in the conditional probability distribution of a class given data, is that P of Ck given x star. We want to find the most probable class Ck given the data x star, right? That means for C star or Ck, we have to find argmax k of Ck given x star, where k ranges from I to capital K. This is small k. And to find Pck given x star, we use Bayes rule, which states that Pck given x star is equals to P of x given Ck, P of Ck upon P of x. This is x star, right? Using this, we have to decide the most probable class or the best fit. As we have seen, to do generative classification, we must learn a class conditional distribution, right, for each of the class K in our data. Now, if our observations are of high dimensions, like if there are many features for xi is made up of, let's say, 1,000 features, these calculations would be very long, right? Now, classifying this kind of examples can be really tough, and finding these distributions can be really difficult for when we have a very large number of features, and it can be really slow as well. So to get a way around it, we have this concept of naive Bayes, right, which gives us a way out of this problem. Okay, so before describing it, let's go back and rewrite the quantity we are trying to estimate, that is P of x given Ck, P of Ck, right? Because we had to find P of Ck given x, the max of it, and we ignore P of x because it is similar for all the classes. So in order to find this, let's write it in terms of x comma Ck. Now x is made up of P features, this can further be written as x1, x2 till xp given ck. So x1, right? You can take this as capital X. If this can be written like this, it can further be written as x1 given x2 to xp comma ck, right, multiplied by x2 x3 xp ck, right? And if you again distribute this, this can again be written as p of x2 given x3 xp ck into x3 till cp, right? Because we are writing this as this. In the end, what we get left with is p of x given ck into p of ck is equals to p of x1 given all the features and class ck multiplied by x2 given x3 till ck, uh, we get left with xp given ck into p of ck if we write it for each feature, and each feature is independent. X2 ck to p of each feature is independent, right? As a naive Bayes introduced the assumption that the features are conditionally independent, therefore xi is independent of xj for a given class ck for all j not equals to I, right? We take this concept of independent features, we apply it over here to get p of x1 given ck, p of x2 given ck goes on to p of xp given ck, p of ck, right? Now this can again be written as multiplication of I goes from 1 to p of xi given ck, right? This gives us the formula for x given ck, p of ck, right? For each class k, for that data point x, we find the maximum probability that satisfies the class. All right, we find the maximum probability, and that probability will give us the class ck to which the x will be assigned to. We'll take up an example, and this formula will be clearer to you. So this is basically feature one given like the example that we did on breast cancer. So xi can be like tumor present given cancer, or radiation present given cancer. So these can be different features of that tumor, right? Similarly, like if you have an example of diabetes, so your blood pressure and your weight and your height can be your features such as xi, and your ck can be if you have diabetes or not, right? Where your blood pressure, your height and your weight are independent of each other, right? So these features can be taken as independent and individually, and can be able to can be used to predict the respective class for the data point. So initially we were doing a p-dimensional distribution, right? Because we were taking x1 given x2 till xp and ck. Now, due to this independence assumption of the features, what we have to do is we just now have to estimate p different one-dimensional distributions, right? For each of the k classes. For each of the k classes, for one of the class, we do these p different one-dimensional distributions, multiply them, get the probability for that class, compare the probability for k classes, find the maximum of it, and the maximum probability will give you the class that data point should be associated with. Now that brings us to spam, ham, and multivariate and multinomial. Now we have seen naive Bayes allows us to write px given ck as to 1 pxi given ck. Right? Now let's take an example of spam and ham emails. So let's take 8 emails, out of which 4 are spam and 4 are ham. Right? These are made up of words which are represented by A, B, C, D, and E. Right? So let's take these two sets of emails where the top 4 are the spam emails made up of words A, B, C, D, and E. Right? So there are 2 classes. Let's represent those classes as spam and ham. Right? These are spam and these are represented as ham. The probability of occurrence of spam and ham emails are both 1/2. Right? Now let's take words D and E as stop words. Right? Stop words as in like you can take them as stop words, or you can take them as most common words like the, is, like which present little to no value to your classification problem. Right? So we ignore these words. So we ignore D and E. We just consider A, B, and C. Right? So on the basis of this concept, I'll explain multivariate and multinomial distributions. And now with the 8 emails, we have described our emails, we have described our vocabulary. Vocabulary is just A, B, and C. We have defined our classes C positive and C negative. Now let's explore multivariate Bernoulli-Nave Bayes. Now let's discuss a multivariate Bernoulli-Nave Bayes, which is one way of encoding our observations. Right? In multivariate Nave Bayes, what we do is we encode each email on the basis of binary feature. That binary feature represents whether a word is present in the email or not. Right? If we take E1, right? Encoding E1, X1 would be encoded as if A is present, no it is not. If B is present, yes it is. X1C, 0. Right, so encoding for E1 would be 0, 1, 0. Similarly, encoding all our 8 emails using multivariate Bernoulli-Nave Bayes, we get, I'll draw a small table here, XIA, XIB, XIC, E1, E2, E3, E4. These 4 are part of spam, whereas E5, E6, E7, E8, these are part of ham emails. Encoding E1. Now, if you remember, we had E1 as BDE, BBDE. So no A is present in E1, which is represented as 0. So this becomes 0, 1, 0. Similarly, E2 becomes 0, 1, 1. E3 would become 1, 0, 0. E4 would be 1, 1, 0. No C present, but A and B are present. Let me draw a small dotted line here. Similarly, if we take E5, we get 1, 1, 0, 1, 0, 1, 1, 0, 0, and none of A, B, C are present in E8. Now, loaded with this table, what we try to find is, we try to find PKJ, which is nothing but basically maximum likelihood. Right, we are not going into too much details here. Now, in order to calculate PKJ, PKJ stands for, okay, a document of class K, the probability of occurrence of word J in a document of class K. Right? If we write it down, it would be number of documents of class K containing J divided by total number of documents of class K, right? So if you want to represent our emails, let's say this would represent letter A or word A being present in emails that are spam. So if we take a look at this example, A is present in 2 emails, right? E3 and E4 out of 4. So 2 out of 4. Similarly, if we take for B and if we take for C, we get for B it is present in 3 emails out of 4, and similarly C is present in 1 email out of 4. And if we take for ham, A is present in 3 emails out of 4, B is present in 1 out of 4, and C is present in 1 out of 4. Now, loaded with this information, right, we have built our classifier on the basis of these 8 emails. On the basis of 8 emails, we have built our classifier. Now, if this classifier sees a new email E star, it would be able to classify this email E star correctly into ham or spam. Right, I'll show you how to use this information in order to encode and classify an email into a separate class. Right, using this information, what we do is, let's say our classifier encounters an email which is given as E star is equals to A B B D E B B. Now, if you encode this, our X star would become A is present, yes. B is present, yes. C is present, no. So our encoding becomes 110. Now, in order to find the correct class C star, what we need to do is we have to find the max probability that satisfies if P of X star given CK. And this would be C star, yeah. Right, for each sample K, right, because each class K, we find the probability and we try to find the max of it, right? So in this example, we'll be trying to find C plus and C negative, right? The probability for that email belonging to C, a spam class or a ham class, right? So firstly, for K equals to positive, we do the following calculations. Right, for K equals to 1, we have to find P of C positive, or K equals to positive class, right? We have to find P of C positive multiplied by P of X star given spam class. Now using naive Bayes, we get C positive X, let's represent this as X star J. Star is basically the word that is present or not given C positive, where J belongs to our V. V is our vocabulary, that is A, B and C. So this is just an identity function. That means if A is present, that means this would be 1. If B is present, this would be 1. If C is present or not present, this would be 1 or 0 respectively. So doing the calculations, we get left with P of XA equals to X star A given C positive multiplied by XB equals to X star B given C positive and multiplied by PXC X star C given C positive. This is nothing but P of C positive. X star A, our encoding was 1, 1, 0, right? So X star A is present. Therefore, P of XA is equals to 1 given C positive into P of XB is equals to 1 given C positive multiplied by P of XC equals to 0 given C positive. This is nothing but P of C positive plus A plus B, and as this is 0, we would get left with this. Now we found the probability of each class is equals to 1 by 2. P of A plus was 2 by 4. P of B plus was 3 by 4. And C plus was 1 minus 1 by 4. This gives us 9 upon 68. Right. Using the same calculation, right, I'll leave the last line. Okay. Using the same calculation for k equals to negative class, we reach the same equation, that is C negative P of X star given C negative would be equals to P of C negative multiplied by A present in negative, B present in ham, and C1 minus C negative. Right. Using this is 1 by 2. A negative was 3 by 4. B negative was 1 by 4. And this was 1 minus 1 by 4. We get left with 1 upon, sorry, this was 9 upon 64. My bad. And this is 9 upon 128. Now seeing this, comparing these two values for C positive and C negative, right, we see that 9 upon 64 is greater than 9 upon 128. Therefore, the class that email would be assigned to is the positive class or the spam class. Therefore, the email that we encountered or the classifier that we built encountered classified that email as a spam email. So now we have seen how to make predictions under the naive-Bayes multivariate Bernoulli model, right? Note that for each prediction, we are multiplying the probabilities with each other, right? Now let's say we present four such spam emails to our classifier that do not contain a word A in them, right? So if they do not have A in them, their table would look something like this, right? E1, E2, E3, E4, these were spam. If there is no A in them, right, this could be anything, right? So if there is no A in them, that means this becomes 0, right? And if this becomes 0, and if we encounter an email with A in, right, we encounter an email which has X star A is equals to 1, right? If this is equals to 1, regardless of the values of other features, right, because we'd have to multiply, if this is present, we'd have to multiply it something like this, but P plus A is 0. So regardless of other features, other values B or C, this will always result in 0. Hence, an email containing A will never be classified as spam, right? So this poses a real problem during classification. So for that, we introduce the concept of smoothing, multivariate Bernoulli smoothing. So in smoothing task, what we do is we modify the formula pkj, tweak it a little bit. What we do is this part remains the same, that the number of documents of class K containing J, right? What we do is we add 1 to the numerator and divide by the denominator remains the same, total number of documents with class K plus possible values of X, right? Or the features, like right now we are taking binary features, right? 1 or 0. So the possible values of X is equals to 2. Therefore, using this formula, using this new smoothed formula, we get new values such as P plus A would become 2 plus 1 by 4 plus 2, that is 3 by 6. Similarly, P plus B becomes 4 by 6. P plus C becomes 2 by 6, that is 1 plus 1 upon 4 plus 2. P minus A becomes 4 by 6. P minus B becomes 2 by 6, and P minus C becomes 2 by 6. This way, it ensures that none of the probabilities is. So basic logic behind it is very, very simple, right? Now, like, let's discuss how we derived this formula, right? What we have done is nothing but, in order to encounter the fact that there can be no words present, a particular word not present in any of the emails, what we do is we introduce two emails on each ham and spam side. Let's say EP1, EP2. Similarly, we have E5 till E8, and we again introduced two files here, right? These two files are nothing but these were like the original self that it was before, 101, 011, and so on. This was 010. This one was 000, right? So there was no A present in it. So what we do is we introduce two files such that one file contains all the words and the other file contains none of the words. Similarly, in the ham side, this is spam, and similarly on ham side, we introduce a file with all three words and a file or an email with none of the words present. So as you can see, number of documents in spam have increased by 2, right? While the number of samples have increased by 1. Similarly for ham, number of documents have increased by 2, while the number of samples for each A, B, and C have increased by 1. Therefore, we derived the new formula for smoothing. So now using these new probabilities PA plus and PB minus, and we use these probabilities in the formulas that we derived earlier to classify new email that we have into spam or ham. Now let's tackle multinomial naive Bayes. Now, as we have seen in multivariate, the only problem with multivariate naive Bayes is that multivariate Bernoulli model ignores the frequency of the words, like, which can throw away very useful information that is required for classification. For example, like in spam or ham, it would be important to know that the word casino appeared multiple times in an email, or the word Viagra appeared multiple times in an email, right? So for that, to encounter that, what we do is we introduce multinomial naive Bayes, which uses multinomial distribution. So in multinomial naive Bayes, what we do is, okay, we take the same example with the 8 emails from E1 to E8. Now, instead of encoding these emails as bit vectors for each word, what we do is we encode these emails as count vectors. So let's say we had XIA, XIB, and XIC. We have 8 emails: 1, 2, 3, 4, 5, 6, 7, and 8. Now let's take our first email, that was E1 was given as a BDE BBDE, right? Now B and E were stop words, so we removed them. Now encoding this as a bit vector, we have no A's, we have 3 B's and 0 C's. Similarly, if we encode our second email, we get 033. For third, we get 300. For fourth, we get 230. So this was the encoding for count encoding for spam. Now we do the count encoding for ham. If we take E5, we get left with 430. E6 would be 403. E7 would be 300. E8 would be none, right? So using this table, using these count vectors, we again try and define our new probabilities for each of these features. Okay. Now you may notice a subtle difference between the Bernoulli model and this multinomial model is that previously we were taking the probability uh, that a particular word existed in a given class or not, right? But now in this we are going to take the probability that how likely a random chosen word in the class is a particular word, right? So instead of p, we will denote this using theta. So we'll get theta a, theta b, and theta c for positives, and similarly for ham classes, right? Where theta kj is number of times. This is little different from the one we described earlier. This is number of times word j occurs in k, right? Upon total number of words in k. We are taking total number of words because we are taking the frequency of their repetition into consideration as well. So in order to find the proper probabilities, we'll need to take the consideration of the total number of words in a particular class. So if you take the table that we described earlier, you would see that for positive class, A occurs 5 times out of a total of 5 plus 6, 11 plus 6, 17. So 5 by 17. Similarly, for positive, uh, in if B occurs in a spam class, we'd get 9 by 17, B 3 by 17, right? And similarly, theta A for negative would be 11 by 17. Theta A for B for negative would be 3 by 17. And theta B C for negative would be 3 by 17 again. Alright, using these values, now our classifier has been built. Now, if it encounters a new email, we need to encode that email as count vector, and then using these values of thetas, we can predict the probability of occurrence of the class. So before we jump into the formula, I would say the probability mass function of multinomial is, it is given as let's say x has 3 features, and we are taking the frequency of occurrence of the features in consideration, right? So you get n factorial upon x1 factorial, x2 factorial till xk factorial multiplied by theta 1 x1 theta 2 x2, similarly this. So using this formula, we'll build the classifier that classifies our emails, right? Now we are not going into details behind the formula. If you want, you can research on your own. So using the values that we have found out, let's say we encounter an email E star, right, where E star, where the encoding for X is given as, let's say it has 4 A's, 3 B's and 1 C's, right? So if I want to use the formula P of C plus P of x star given C plus would be equal to P of C plus into 4 plus 3 plus 1 is equals to 8. So 8 factorial upon 4 factorial into 3 factorial into 1 factorial multiplied by theta a to the power 4 into theta b to the power 4 into theta c to the power 4. Oh, my bad. Theta b to the power 3 and theta c to the power 1. Right? Where this is plus because we are considering the positive class, plus and plus. So this gives us 1 by 2 into 8 factorial upon 4 factorial into 3 factorial into 1 factorial multiplied by 5 by 17 to the power 4 into 9 by 17 to the power 3 into 3 by 17 to the power 1. Alright, you can simplify this, find the result. Similarly, find for negative PC minus, right? Compare the result for positive and the negative. Whichever is smaller, just assign your email to the respective class. Now, in this also, um, if the frequency of occurrence of a word is 0, we might face a problem, right? So what we do is we introduce the concept of smoothing in multinomial as well. So in multinomial smoothing, so a theta kj becomes number of times word j occurs in k plus 1 divided by number of words in k, right, plus mod of v. What is this mod of v? V was our vocabulary, that was a, b and c, and the size of vocabulary would be 3 in this case, right? So our new thetas would become 5 plus 1 by 17 plus 3, which is equals to 6 by 20. Theta plus b would become 10 by 20. Theta plus c would become 4 by 20. Theta minus a would become 12 by 20. Theta minus b would become 4 by 20. And theta minus c would become 4 by 20. So using these new values and the formula that we discussed earlier, we can build a new classifier, the smoothed classifier, and which is even able to segregate documents even if the frequency of occurrence of a particular word is 0. Now, if you want to visualize smoothing, in the Bernoulli case, what we did is we introduced two documents, one containing all the words and one containing none of the words, right? EP1 and EP2. In this case, what we do is we introduce three documents, or the number of documents, the number of classes that are there, right? There were A, B, C, three distinct features that we are taking, or three distinct vectors that we are taking. So what we do is we introduce three documents such as V1, V2, V3, each made up of just one word occurring just once, right? We add these three documents to spam and add these three documents to ham as well, right? Therefore, we get the formula of plus 1 upon the total number of words. X is the total number of words, or the total number of times J occurs in class K, where upon capital X is the total number of words in class K, plus 1, 2, 3, right? So this is how you get the smoothing formula. So thank you, and this is all for today. I'll see you next week.